Disappointing?
If you don't
Yeah,
have
they're probably gonna ruin it.
I've never watched Star Wars.
They already ruined it with the last three. These will be better.
They better be, or
All right.
assume.
10 to the 18th stars. That's a lot. That's the observable universe,
I eat more.
which basically means our galaxy contains about 100, anywhere from 100 to 400 billion stars. And through our telescopes, we can see somewhere on the order of 100 to 400 billion galaxies.
So multiply them together.
Multiply those together, and you got 10 to the 18th. That's a lot. And it may be even more than that. Because you'll see there's a lot of stars that aren't even visible. So, how do we know how far a star is away? If you're looking in the sky and you just see a star, how can you tell how far it's away?
Triangulate.
One way is by triangulation and parallax. And do you remember we talked about parallax before? If you open your left eye and then you open your right eye, your finger kind of shifts locations. That works with a star too, if it's a pretty close star. Instead of opening your right eye and your left eye, you take a picture when the Earth is over here on this side of the sun. 6 months later, you take a picture when the Earth's over here on this side of the sun. And compare the two photos to see if it's switched places compared to the background stars. That shift is sometimes very tiny, but it can be measured with computers. And they can calculate the distance that way. How sweet is that? Astronomy rocks. What's that?
Aren't they? Moving, but at like all times away from us.
They're moving, but the movement is so slight that it won't make the difference in the calculation. The movement is great if you're near it, but it's so far away that it's little bit of movement, which is called true movement, doesn't affect what happens in 6 months as far as the distance calculation.
Can't they just take continuous pictures over the 6 months? They can triangulate many times.
Yes, they can. There are satellites dedicated to the sole purpose of only that.
Sounds like a plan.
And so what they're doing is they're finding the distance to all these stars and they're plugging them into a computer map, a three-dimensional map that tells you where this star is, and how far they are away. There's this three-dimensional map of the universe being built. Isn't that cool? So we have a word, a parsec. You may have heard of this before. A parsec is the distance a star must be from the sun for its parallax to equal 1 arc second. So if the shift is 1 arc second, do you know what an arc second is? We have 180 degrees.
1/360th of a degree.
1 degree is a very small bit of shift. And then 1 minute is 1/60th of 1 degree, and 1 arc second is 1/60th of 1 minute. So you're talking about a little shift. A little tiny shift. If the star shifts 1 arc second, then we say that the star is a parsec away. And a parsec is equal to 3.3 light years. That means if it shifts 1 arc second, we know that star is 3.3 light years away. That means if you were traveling in a spaceship at the speed of light, you would get to that star in 3.3 years. So a parsec is a unit of distance. I remember that was a Science Bowl question I got right when I was in high school. They said parsec is a unit of A, and I buzzed in, I didn't even need the choices. Distance. Okay. Enough about my greatness. Here's the thing, there are no stars that close. There are no stars within 1 parsec of our star, except for the sun. The sun is very close, but outside the sun, there are no stars within 3.3 light years. The closest star is about 4 light years. And that's called Alpha Centauri. You ever heard of that? Or actually, the closest star is called Proxima Centauri. It's part of the Alpha Centauri complex of 3 stars. Alpha Centauri is actually 3 stars that are moving around. And the one that happens to be nearest us right now is called Proxima Centauri. It's about 4 light years. So every parallax shift of every star they can see out there is less than 1 arc second. Less parallax shift than 1 arc second means further away. The smaller a star's parallax, the farther it is away. So here's a diagram of that. So January, you take a picture. July, you take a picture. The star compared to the background stars will be in a different location. In January, you see that star with these stars behind it. And in July, you see that star with these stars behind it. Those background stars are very far away and don't shift at all. And so there's the angle right there. If that angle is 1 arc second, we know the star is 3.3 light years away. If that angle is less than 1 arc second, the star is even further away. Here's the star in January. Here's the star in July. So, our nearest neighbor is Proxima Centauri, a member of a 3-star system known as Alpha Centauri. 1.3 parsecs, or 4.3 light years away. I was saying 4 light years, 4.3 light years. That's a good trivia question there. What's the nearest star? What they'll ask you is, what's the nearest star to the Earth? And people who think they know go Proxima Centauri, and it's not, it's the sun. So they tricked you, see? But what's the nearest star to our sun? Proxima Centauri.
Proxima Centauri.
What's like the official name for the sun? Is it the sun?
The sun.
Really?
That's the name. Beyond Alpha Centauri, there's a star called Barnard's star. It's 1.8 parsecs, which is 6.0 light years. You just take the amount of parsecs and multiply it by 3.3 to get the amount of light years. So wait, let me give you a quick calculation. If a star is 100 parsecs away, how many light years is it away? 100 times 3.3, 330. Scott, you in the front. Yes?
How long would it take our spaceship to get to, like, the closest star?
That's a cool little math problem. You want to do it?
Sure.
It doesn't take long. Our fastest ships, if we use gravitational slingshots around planets, we could get them going 30,000 kilometers per second. Wait, no, that's not right. 30,000 kilometers per hour. That's a lot different. So,
Divide that by 360.
you want to get to kilometers per second? So we multiply by, let's put hours on the top to get rid of our hours, and put seconds on the bottom. So, how many seconds in an hour? Do you know?
Would it be like 9,600,000?
right
Well,
now.
no, I
They're 3,600 seconds in 1 hour. So, does anyone have a calculator handy? No one?
What, 10 million feet?
So
500.
30,000 divided by 3,600. That's 8.3 kilometers per second.
That is probably going to take like 20,000 years.
So, if a star, let's say the nearest star is let's just say 4 light years away. Light travels at 300,000 kilometers per second. So if you're doing 3.3 light year, if it's 4 light years, so how many seconds are in a year? We know there's 3,600 seconds in an hour, and how many hours in a year?
Times 24.
Times 24
Times 3.
hours in a day, times 365 days in a year. We get how many kilometers away is the nearest star? 300,000 times 3,600 times 24 times 365. 9.4 times 10 to the 12th kilometers. And we go 8.3 kilometers per second. Divided by 8.3. It'll take us 1.4 times 10 to the 12th seconds. So how long is that?
A couple thousand years.
Divided by
Couple
3,600 will give you the hours. Divided by 24 will give you the days. And divided by 365 will give you the years. It'll take 36,000 years for a spaceship to reach the nearest star. That's a great problem that you should all need to know how to solve. That's good. Yeah. Ellie, every day with you.
It's not every day.
Is it every day, class?
It's every other day.
Oh, that's not every day. Then I take
Is that okay? Let's say that means no tomorrow.
Go to the bathroom tomorrow. No, your door just shocked me.
Oh, it shocks people who go to the bathroom. Here is a model of the nearby stars and where they're located based on this map that they've made. This is just some of them. This is not all of them.
What's with the sun being so much farther away from everything else that is, like, those two stars, like in the bottom right there, are so close together?
Yeah,
What's with that?
I don't know. It's just the way it is. There's a lot of stars that aren't close to anything else, just like the sun.
It's cheating.
But there are some stars that are close. Like Alpha Centauri is 3 stars. Wouldn't it be a different world if we had 3 stars that we were going around? It would be kind of like in Star Wars, where there's just a double sunset. Do you remember that? In Episode 4, A New Hope? Come on.
Why are some of them white and the others purple?
Well, stars have different colors, and we're going to talk about stars' colors next.
Are they all in the same like plane?
No, that's what this is trying to show. Like, here's our sun. If this is the north of the sun, and this is the south, according to how the Earth is going. So Alpha Centauri is actually in the southern hemisphere faces Alpha Centauri. So we aren't really able to see the Alpha Centauri from up here in the northern hemisphere. You got to go down to South America and look at it at night. Look at night to see it. You might be able to see it depending on the season, a little bit of it, but it would be low in the sky. And so they're trying to show you here, like this one is out and up a little. This one is this way and up a little. That's what this is trying to show you, what plane they're in. So they're scattered about. We call that our local neighborhood. There's what it looks like through a telescope, and that's highly magnified, so that's not really what it would look like in the sky. It's actually not very bright.
behind that? Are those other?
These
stars?
are background stars that are really far away. And again, with the naked eye, you don't see any of these because your eye can't pick up anything that dim. This is Alpha Centauri seen through a telescope that's picking up a lot of light. So the better your telescope is, the more light you can pick up and you can see these background stars. With the naked eye, you can see Alpha Centauri with the naked eye, but that's all you'd see is that, and none of this around it. So if you ever do travel to the southern hemisphere, you look for the Southern Cross, which is 4 stars that are pretty visible in the sky, and Alpha Centauri is near it. Have you ever heard of the Southern Cross? There's a James Taylor song. Southern Cross. Out of town on a boat to the Southern Islands. Huh? Good song. James Taylor. Look, everything can't be widespread panic. I'm sorry.
I like James Taylor.
That's another band.
I know.
Everything can't be Limp Bizkit.
No one? No.
I know.
Fast forward like 20 years.
Justin Bieber.
Everything can't be Justin Bieber.
No. Pick someone else.
Everything can't be Britney Spears.
No.
She's old too.
No, Britney Spears.
Who's new?
Madonna.
Madonna, no, she's real old. She's as old as I am.
50.
She's still
All right. Now, hey, somebody was saying about proper motion. Carson was saying about proper motion of stars. I call it it's proper motion. Stars are moving in space, and you can detect their motion by the Doppler effect. Or, like you were saying, taking 2 pictures at different times. Take a picture of a star, and a year later take another picture, and see if it has moved in proper motion. And the way to do that is to take the picture from the same spot. In July you take it, July 1st, and on July 1st the next year you take it. So the Earth is relatively in the same spot. Even though our sun is also moving, and that has to be taken into consideration. But by doing this, if it's done correctly, you can find the proper motion of a star. And the fastest moving star that we know of is pretty near to us. It's called Barnard's star. And it's moving at 88 kilometers per second, which is a lot faster than our spaceships go. Star just flying through space. So stars do all have what we call proper motions to them. They are moving through space. And it's not much, but over hundreds or thousands of years, you do see a change. The Big Dipper, if you look at it, it has a certain look to it, but in another 100 or 200 years, that look will change. And over thousands of years, the change can be pretty big because the stars are moving. So it won't look like a Big Dipper in several thousand years.
It looked like a 16th century later.
Yeah, I don't know what it'll look like. I think there are pictures that show what it'll look like later. They've done those calculations. So here we are, and we know it's 1.3 to Alpha Centauri, but Alpha Centauri is actually moving in space at 31 kilometers per second. And they figured that out by math. They know the distance, they know what direction it's going, they can figure it out. Supposedly y'all have done problems like this in physics. True?
What kind of problem?
Where you have the motion of something and you know the angle to it and you know how fast it's moving. Vectors, have you done vectors?
Yes.
This is vectors.
Oh, yeah.
We did Kepler's laws.
You know, if you have a vector this way going 24 In this way, going 20, you can figure out the resultant. Yeah, you've done this. So this is physics for those of you who haven't taken it. You figure out physics problems like this. So if you look at this little dot, that's Barnard's star. Taken at one point of time, and here it is at a later point in time. You see it has moved. If you use the reference point of this star here, it is moving upward. It's moved upward in reference to that star. It takes a keen eye to notice any difference between the two pictures, but computers can do it no problem. So those two pictures were taken 22 years apart. So that dot moved from here to here in 22 years.
What is that like ginormous dot on the side?
That's a different star.
Why would they not track that one? Why did they track that?
Because that one's not moving very fast.
Oh.
And it's a lot further away.
They moved a little bit.
Did it move?
Yeah, you can tell. See, on the one on the right, it's like touching the edge, and on the one on the left, it's not.
Yeah, you're right. It did. It just moved a little bit. But not as much as this one. This one's moving more.
How would that
Is
work?
our sun moving?
In the near
Yes.
bottom.
All stars are moving. What's that?
Actually, never mind. I just
No.
went for me to point at it.
Where's the sun moving?
Please answer our question.
I don't know where it's moving.
As our sun moves, like our planets move, like, right?
Our planets move with it, so it's not moving away from us or towards us. Our planets are moving with it.
One of the stars disappeared.
Really?
Yeah.
They probably got better, like, telescopes.
Yeah, it could have been. I don't know. Or maybe it was an asteroid or something in the way. Who knows?
It probably got destroyed.
So, have you all learned about the inverse square law?
Apparently, we learned about it in chemistry, but I don't remember.
Here's how the inverse square law works. Twice the distance equals 1/4 the brightness. And this works with anything. A flashlight that I'm holding to you. If I'm holding it here, you've probably dealt with this when the cops pull you over. If I'm holding the flashlight here, and I get half the distance, that doesn't mean it's twice as bright. It means it's 4 times as bright. Half the distance is 4 times the brightness. Twice the distance is 1/4 the brightness. It works as squares. So if I get 3 times the distance, it's 1/9 the brightness. Because you just square it, you see. 3 squared is 9. 3 times the distance, 1/9 the brightness. So we can use this calculation to help figure out things about stars. Distances and brightnesses and such. And this is a figure showing, okay, if you're 1 unit of distance from the light source, it covers 1 square. But if you go 2 unit of distances, it now will cover 4 squares. And if you go 3 unit of distances, it now will cover 9 squares. This is just one of the laws of physics.
Is it because the light isn't concentrated quite like in the
Yes, it's the same amount of light spread over a larger area. And it spreads out in 2 dimensions instead of just in 1 dimension.
Okay.
So the extra dimension adds an extra factor of multiplication, and that's why it's squared. A little video about it. Enable all, even though it's not recommended, but it doesn't really scare me. Pretty tough. Alan Sill, show us your 3D modeling. Oh, this is terrible. Okay, here we go.
Spreading over progressively larger surface areas. The light intensity varies inversely as the square of the distance from the source.
This is not good, is it?
Gravitational attraction between 2 astronomical bodies follows a similar inverse square law for the same mathematical reason. This animation shows how the area covered by the light grows with the square of the distance and how light is spread out over that area as it moves from a point light source.
So as the same amount of light is spread out over a larger and larger area, it gets dimmer and dimmer. And gravity works like that
From a point
too.
light source.
Gravity is an attraction. Magnetism works like this too. So if you get twice as far from something, you feel 1/4 the gravity of it. Or magnets. Have you ever noticed that magnets are real strong when they're close together, but you get them far apart and there's not much attraction there? Two stars of differing luminosities can appear the same brightness based on their different distances from the observer. So this is important for you to understand. If I have two stars out there in space, and one is brighter than another, that could mean two different things. They're the same brightness, but one is closer, and that's why it's brighter. Or they could be the same distance, and one is just brighter, because stars come in different sizes and different brightnesses. So scientists have to be able to figure this out. If we put a giant head in space, first it's kind of scary, and then you just look at what it's saying. There's star A, and there's star B. Star B is way brighter than star A. But they look the same to the giant head floating in space, because the giant head is closer to A than it is to B. You see? The giant head is much larger than both stars. There's really no such thing as a giant head in space, y'all. That's representing somebody living.
Oh, really?
Yes. Okay, so what they've come up with is what we call a magnitude scale. It was set up by this dude named Hipparchus. And he said, I'm going to make a scale, and I'll say that the brightest stars, I'll call those first magnitude, and the dimmest stars I can see are going to be called sixth magnitude. And he went outside every night and he looked at the star, and just based on his eyes, he gave it a number. Like he said, okay, this star, I can barely see that. That's sixth magnitude. That's the brightest star in the sky over there, Vega. I'll call that first magnitude.
When was it that he did this?
That is an excellent question. 1700s, 1800s? I don't know. No, Hipparchus. He was Greek. So that's way back in BC.
So how much information did he have on this stuff? What would he have known about the stars before doing all this?
Nothing. He's just looking at them. And they had names for all the stars. So this one, he'd write the name, and then he'd write how bright it looked. So they used the same scale that he started. They still use that scale. But they've now made it more scientific by actually measuring the brightness with machines. And even though you don't have all this down, I'm going to switch so you can see the scale. And they've extended the scale from 1 to 6 all the way from 30 to negative 30. And so as you go down in magnitude, you go up in brightness, which is confusing. So the naked eye limit is 6. That means anything with a greater number than 6 is too dim for the naked eye to see. That was according to Hipparchus' scale. So our sun is really bright, so it goes really low. It's negative 26.7 on this scale. The full moon also bright. Venus also bright. So anything negative is real bright. The Hubble can see stars so dim that they are 30 on the magnitude scale. So Hipparchus was saying the dimmest thing he could see was a 6 magnitude. The dimmest thing the Hubble could see is a 30 magnitude. Your binoculars can see all the way up to 10 magnitude. Have you ever taken a pair of binoculars outside at night and looked at the sky? You can see a lot more stars. It's a pretty amazing thing to do. Do it. Do it tonight. You'll be like, whoa. First time I did it, I was like, oh my gosh. A man made me do it, a doctor friend of my dad's who died recently. What was his name? He called me up and he said, take your binoculars out. I was like, I don't want to. And he made me do it and I was like, cool. What's his name? I'll think of it. Burgess Walker, Dr. Walker. Anyone know the Walkers? No. The kids went to the school. What'd you do? Jenny Walker? You want to know Jenny Walker? Her dad. Jenny Walker. She had a brother, Jared Walker, who also died.
Did she graduate from here?
Mm-hmm.
Was she born?
Mm-hmm.
Did she graduate in like 99?
Yeah, about that.
I think she was in my uncle's class.
She was in your what?
My uncle's class.
Oh, really?
James.
Yeah?
Yeah, I know.
Yeah. Her dad was a cool guy. He turned me on to astronomy. So, there's one more measurement that they call absolute magnitude. Absolute magnitude is a number you give to a star that tells how bright it actually is. Not how bright it looks to us, but how bright it actually is. And so what they do, they say, if we set a star in space and we get 10 parsecs away from it, how bright will it be? And that's called the absolute magnitude. So our sun looks really bright to us, but it doesn't have a high absolute magnitude. Because compared to other stars, it's not that bright. It's the average. There are some stars with a much bigger absolute magnitude. And we'll talk about those tomorrow. They're called giants. Peace out.